Okay, everyone, we're going to look at number 21 in section 4.3. We have this function here that we're going to find the critical points for, and then, of course, do the first derivative test, check for local maximums, and find the intervals where it's increasing, decreasing. Just a quick note, the domain of this function is all real numbers except for 0, right? And at 0, we have a vertical asymptote if you were to have graphed this function. And that's important. When we're doing a sign check, we will probably want to check on either side of that vertical asymptote. Okay, so we need to find the derivative to find critical points. And so notice this is a quotient. And so I'm going to use the quotient rule. Take the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Derivative of x we know is 1. E to the 5x derivative is by the chain rule, right? Derivative of the outer function is e to the u or e to the 5x times the derivative of the inner function 5x is 5. So when I multiply that out, I get this expression. And now I can factor up top the e to the 5x out, leaving a 5x minus 1. And so when is this derivative going to be 0? Keep in mind that x cannot be 0 in the original function. So even though the derivative is undefined when x equals 0, but that's not a critical point because it's not in the domain of the function. E to the 5x is always positive, right? This part is always greater than 0. And so the only time the derivative will be 0 is when 5x minus 1 is 0. And that occurs right when x is 1/5. So that's our critical point. We want to do a sign check now on that derivative here. And I'm going to put in there the 0 right where we're undefined. Of course, that's corresponding to a vertical asymptote for the graph of the function, the original function. But the derivative, of course, is undefined there as well. 1/5 where 0. So I plug in something less than 0, like -1. And notice when I plug in any number, e to the 5x is always positive. X squared, right, is always positive for any non-zero number, right? That's always greater than 0. And so the only thing that really matters is what's the sign of 5x minus 1? Well, if I plug in a -1, I get -5 minus 1. That's -6. It's negative. If I plug in something between 0 and 1/5, 1/5 is 0.2. So half of that is 0.1 or 1/10. If I plug in 0.1 or 1/10 to 5x minus 1, I get 1/2 minus 1, which is negative. And so again, we're negative there. If I plug in something bigger than 1/5, like say +1, then this would be 5 minus 1, 4, positive, right? So everything's positive and we're positive now. And so I can answer the questions. Functions increasing on the interval where the derivative is positive. So from 1/5 to infinity. We're decreasing, and I'm going to do these two separate intervals because there's a break there because of the vertical asymptote in the original function. So I'm going to do from -infinity to 0, and then from 0 to 1/5 where the derivative is negative. And then notice we have a sign change in the derivative at 1/5 from negative to positive. And so we have a local minimum at x equal 1/5. And there's no local maximum. Just a quick note that you could have had a sign change in the derivative over the vertical asymptote, but the vertical asymptote, this would not be a location of a local max or min. Remember, local max or mins occur at critical points, which are points in the domain of the function, right, where the derivative is 0 or undefined. So again, this 0 makes the derivative undefined, but it's not in the domain of the function, so that can't possibly be a critical point. Okay, so hope this is helpful for everyone. If you have questions, as always, let me